Imagine this. You're watching Christopher Nolan's Interstellar, and Matthew McConaughey's character is plummeting into a massive black hole. The screen warps, time slows to a crawl, and suddenly, you're questioning everything you know about reality. What if I told you that the very fabric of space and time, the stuff that makes up our universe, might not be as solid as it seems? It could be an illusion, emerging from something way deeper and weirder. Today, we're diving into one of the biggest debates in modern physics. Is space-time fundamental, or is it emergent? Buckle up, because by the end of this video, your mind might just bend like that famous scene in Inception, where the city folds in on itself. If you're into mind-blowing science, hit that like button and subscribe so you don't miss out on more cosmic adventures. Let's start with the basics. Space-time. It's that four-dimensional mashup of space and time that Albert Einstein introduced in his theory of general relativity back in 1915. Picture it like a trampoline. Planets and stars are heavy balls that sink into it, curving the fabric and making things like gravity happen. That's why Earth orbits the Sun, not because of some invisible force pulling it, but because the Sun warps space-time around it. Real-life example? Your GPS on your phone. It has to account for time dilation. Clocks on satellites tick faster because they're farther from Earth's gravity well. Without relativity corrections, your Uber would be off by miles every day. But here's where it gets trippy. Quantum mechanics, the other pillar of physics, deals with the tiniest stuff: particles, waves, and probabilities. It says the universe is fuzzy at small scales, full of uncertainties. The problem? Relativity and quantum mechanics don't play nice together. Smash them into each other, like at the heart of a black hole, and you get nonsense. That's why physicists like Brian Cox, Neil deGrasse Tyson, and others are asking, maybe space-time isn't baked into the universe from the start. Maybe it's emergent, bubbling up from a more fundamental layer of reality. Emergent properties are everywhere in nature. Think about water. A single H2O molecule isn't wet. Wetness emerges when billions of them slosh together. Or consciousness. Your brain's neurons fire individually, but together they create thoughts, feelings, and that urge to binge-watch Netflix. In physics, the idea is that space-time emerges from quantum information, or entangled particles. No built-in grid of space and time. Instead, it's like a hologram projected from a deeper code. Remember that scene in The Matrix where Neo sees the code behind reality? That's kind of what we're talking about. Physicists theorize the universe might be a vast quantum computer with qubits, quantum bits, as the building blocks. Distance, time, even geometry? They pop out from how these qubits tangle up. Speaking of tangling, let's talk quantum entanglement. Einstein called it spooky action at a distance. Imagine two particles linked so that measuring one instantly affects the other, no matter how far apart. In Star Trek: The Next Generation, they use subspace for faster-than-light comms. But in real quantum physics, entanglement doesn't let you send messages faster than light. It preserves causality. No cheating the speed limit. Real-life example: quantum computers use entanglement to solve problems way faster than classical ones. Companies like IBM and Google are building them right now, potentially revolutionizing drug discovery or cracking encryption. But in the context of space-time, entanglement might be the glue holding it together. Picture space as a sea of virtual particles popping in and out, all entangled. That network creates the illusion of smooth space-time. Now, enter black holes, the ultimate cosmic enigmas. In Doctor Who, the Doctor zips through time and space, but black holes are where physics breaks. Stephen Hawking showed they evaporate over time through Hawking radiation. Virtual particle pairs appear near the event horizon. One falls in, the other escapes, making the black hole lose mass. But here's the paradox. What happens to information that falls in? Quantum rules say information can't be destroyed. It's like the universe's conservation law. Burn a book, and in theory, you could reconstruct it from the smoke and ash particles. Same with black holes. If info vanished, it'd violate quantum mechanics. Enter the ER equals EPR conjecture, proposed by physicists like Leonard Susskind and Juan Maldacena. ER stands for Einstein-Rosen bridges, wormholes, those hypothetical tunnels through space-time. EPR is Einstein-Podolsky-Rosen, the paper on entanglement. The idea? Wormholes are just super-entangled particle pairs on steroids. In Avengers Endgame, they use quantum tunnels for time travel, but ER equals EPR suggests wormholes stitch space-time together at a quantum level. Visualize this. The MCU's quantum realm is a trippy subatomic microverse where normal space-time rules break down. Time dilates strangely, and it's full of possibilities. While the movie doesn't explicitly reference ER equals EPR, the scene loosely evokes it. Going subatomic plunges you into a deeper quantum reality, where entanglement could manifest as wormhole-like shortcuts, or the emergent fabric of space itself. Ant-Man's uncontrolled shrink traps him in this entangled, non-local quantum foam, connected to our world via invisible bridges rather than truly destroyed. It's Hollywood flair on cutting-edge ideas like emergent spacetime and entanglement creating geometry. Now, two black holes entangled could be connected by a wormhole, allowing information to escape during evaporation. No loss, just scrambled data carried away by radiation. It's like encrypting a file. The info's there, but you need the key to read it. Wormholes aren't just sci-fi fodder. In real physics, they're solutions to Einstein's equations, but unstable. Remember the Stargate series? Jumping through wormholes to other worlds. If ER equals EPR holds, the universe might be riddled with microscopic ones, emerging from entanglement. This could resolve the black hole info paradox. As the black hole shrinks, entangled pairs pull info out bit by bit. But what about time travel? In Back to the Future, Marty McFly zips to the past and almost erases himself. Hawking's chronology protection conjecture says nature forbids time machines to avoid paradoxes. Even if wormholes exist, you'd need exotic matter, stuff with negative energy, to keep them open. And that's not easy to come by. Real-life parallel. GPS again. Satellites experience time dilation, living slightly in the future compared to us on Earth. It's tiny, but measurable. Causality is key here. Quantum mechanics is causal at its core. No effects before causes. If space-time emerges from quantum stuff, causality might be built in deeper than we think. Think about traffic jams. Individual cars follow rules, but the jam emerges from their interactions. You can't blame one car for the whole mess. It's collective. Why does this matter? Understanding emergent space-time could unlock quantum gravity, the holy grail unifying relativity and quantum mechanics. String theory, loop quantum gravity, these are contenders. In the Big Bang Theory sitcom, Sheldon obsesses over string theory. It's complex, with extra dimensions curled up small. Real-world impact? Better models of the Big Bang, where space-time might have emerged from a quantum foam. Or cosmology, dark energy ripping space-time apart. Is it fundamental or emergent? Even everyday tech, quantum sensors for ultra-precise measurements like detecting earthquakes or navigating without GPS. Let's tie in more pop culture. In Stranger Things, the Upside Down is like a parallel dimension bleeding into ours. Echoes of multiverse ideas from quantum mechanics. Or Inception's dream layers,
when we're asleep,
where time stretches differently, mimicking relativity. A real-life analogy, social media. Your feed emerges from billions of entangled posts, likes, and algorithms. No single tweet defines it, but together, it shapes your reality bubble. Similarly, space-time might emerge from quantum tweets, bits of info linking up. As we wrap up, remember, this isn't settled science. Experiments like those at the Large Hadron Collider probe quantum gravity hints. Future telescopes might spot Hawking radiation from tiny black holes. Useful takeaway. Next time you watch a sci-fi flick, appreciate the real physics inspiring it. Question reality. It's healthier than you think. For instance, meditate on entanglement. In a connected universe, your actions ripple out. If this blew your mind, drop a comment. What's your favorite sci-fi space-time twist? Share this video and subscribe for more deep dives. Thanks for watching. See you in the next dimension.